Good afternoon, everybody. Welcome back to the online seminar series, Machine Learning Needs Mathematical Optimization. So today we have, again, a duetto. So Professor Hochbaum and Jonathan Bodine are presenting together today. They both come from UC Berkeley. Professor Hochbaum is the Chancellor Professor of Industrial Engineering and Operations Research at the Department of Industrial Engineering. Her expertise is very broad. It ranges from integer programming, discrete optimization, network techniques, clustering, image segmentation, etc., etc. In 2004, Dorit was awarded an honorary doctorate of science at the University of Copenhagen. In 2005, Dorit was awarded the Informs Fellowship title, and in 2014, she was selected as a Science Fellow. And Jonathan Bodine is working with her on decision trees, and we are going to talk. We are going to listen to them. And as usual, we leave the questions at the end. But if you really have a very urgent question, please put it on the chat, and I will read it to them. Thank you very much to both of you for joining today so early in the morning. And the floor is yours, Dorit.
Thank you. Thanks for the nice introduction. Good morning, everyone. This presentation is about a new type of decision tree that we call the max-cut decision tree. So decision trees are widely used in classifications. So they use as decision trees by themselves in machine learning or as building blocks of random forests. There is a popular implementation of decision tree that is used that's called CART, and it goes back to Brayman of 1984. We devise here a new type of decision tree that we call the max-cut decision tree that modifies the feature space and modifies the standard splitting criterion. The max-cut decision tree, as you'll be seeing today, provides increased accuracy and decreased running time for training decision trees. So what is decision tree? It is a tree where at each node there is a selection of a feature and respective threshold that is best according to the splitting criterion. And once one selects a feature and the threshold is the value of assigned to the feature used to partition the observation into two sets. One set or one subset is those that have the feature value less than the threshold, and the other have the feature value greater than the threshold. So here you get an abstract manifestation of a tree. So at node 0, or what's called the root node, we are going to scan all the features and for each one the threshold value, and we'll choose one according to the splitting criterion, which is best. And then let's say it's feature I, then all the objects in the data sets that have the value of feature I greater than the threshold go to one set, and the others go to another set. And here, suppose in one of the set, all of them are class A, the same class, it's a pure set, then this is a leaf of the tree. We fathom it and not continue. The other one, we apply the same criterion again and select among the features with respect to that subset of nodes, of objects, the one feature J, so and the threshold J that optimizes the splitting criterion, and then again we select feature J greater than the threshold. This is the one selected, and we split it into sets, two subsets again. So it's a binary tree that you get. So the splitting criterion is the rule used for selecting one feature and the respective threshold among the features. So the commonly used splitting criterion is called Gini Impurity, and this is what we'll call the baseline, what we'll compare to, and this is used by CART. So given a partition to two parts, the way the Gini criterion works is that the fraction of we get two parts, and in each part we compute the fraction of the observation in class C times 1 minus P of C, and we add it up for all the classes. So in the binary case where we have two classes, there will be two items in this sum, two terms in this sum, and we select a threshold for that feature so that the average cardinality weighted average Gini impurity of the two sides is minimized. That's the Gini impurity. Here is an illustration of that. So suppose we have one feature and three objects in the data sets that have the value -1, 2, and 3. So whenever we have n items, the number of possible partitions is n-1 because we can place the partition between any two pairs. So now we compute that, and for this partition, the left side has just one item of the green class. So it's 1 times 1 minus 1, and 0 plus 0 times 1 minus 0. So the value is 0 for this side of the partition. For this side of the partition, we have one of each type, class A and class B. So we have half times 1 minus half plus half times 1 minus half, which is half. So we calculated that for both sides. And now we calculate the weighted average, which is a third. This one has 1 out of the total of 3 objects, so a third times 0. And this side that has the value half has 2/3, so we add 2/3 plus half, and that's equal to a third. So we say the Gini impurity value for this feature is a third, for this feature and this threshold. So now let's try the second possible threshold here, and here the calculation is this side has 2, and the value is half times 1 minus half plus half times 1 minus half. On the right, it is 1 times 1 minus 1 plus 0 times 1 minus 0, which is 0. So we have exactly the same values, and now we calculate the next step. So it's 2/3 times a half plus 1/3 times 0, which is 1/3, which is exactly the same as we had for the previous one. So both possible partitions have the same value, and the Gini impurity will be indifferent between them. And it will choose, by the same manner, it will check other features if there are any and choose among them the one to give this least value. Let's look at the new splitting criterion that is proposed here. So we call it max cut, and the reason is that we are going to look at the actual distances between the objects. So the way this works is let xij present the value of feature j for object observation I, and yi present the class of observation I, and theta presents a threshold value. So for each threshold value, we are looking at the respective partition, and all the same as before, at all the items that are greater than the threshold value and all those less than or equal to the threshold value. And for each pair like that, we consider if they belong to different classes. So if I has a different class than j, then we look at the distances between them. So these are two items, I and j, that end up in different parts of the partition, and we add the distance between them if they are not in the same class. So we are trying to maximize the differences between the two parts of the partition. So as opposed to the Gini impurity, where only membership in each side of the partition counts, here the actual distance or difference counts. So the same example as we had before, if we use the max CART criterion, let's take the first partition possible. So here we have the partition of the green on the one side and the other green and yellow on the other side. And the value here is we take for the green and the yellow, which are in different classes and different parts. We take the distance between them. This one is valued 2, this one is valued -1. So the distance between them is 3 times 1. So the value of this partition is 3. The value of the max CART for this partition is 1. Since we take this green and this yellow, the distance between them is 1 unit. So the max CART is going to consider the comparison between the first and the second, and we want to maximize. The first was 3 and the second was 1, so therefore the second was 1 and the first was 3, so the first one is selected. So this will be the partition selected, and as you see, though both of them are the same in terms of the impurity, each one has one side that have a singleton and the other side has one of each. But these two that are different from each other, at least they are close to each other. So they are close and similar in the feature space. Another aspect of the decision tree is how to represent the feature space. Now we are looking at 4 different feature space representation, and the standard one is just to embed the object in the original feature space, and that's the one that is done in CART. Then we are looking instead at what we call pre-PCA. So PCA stands for Principal Component Analysis. So pre-PCA feature representation, we are going to take the PCA, the principal components of the feature space at the root node. So before we start, instead of working with the original feature space, we work with the principal components. And we'll take all the components, so we don't drop anything, although this could be a consideration of another variant. But here we take all of them. Then we have what we call local or node PCA feature representation, which is the same idea, but here we calculate at each node of the tree with respect to the given subset of objects, we calculate the PCA. Or the last and the fourth option that we are using is to take local or node means PCA feature representation. And here, instead of working with entire set of objects at the given node, we calculate the mean of the not in class. So for each class, we calculate the mean of all the objects that are not in that class. And then we take the PCA of the means. So for instance, if we have K classes, we are going to have K means, each one is a vector, that is the mean of the not in class, and then we are taking the PCA of these K vectors. And in some way, as you'll see, it's really a very successful approach, and it captures the differences and the similarities in the feature space. Okay, so let's start from the first one. The original feature space presentation. I illustrate it on an example. So let's say this is embedded in a two-dimensional space. So we have two features, and the green will be class A and the yellow will be class B. So we have two classes, and we have these clouds representing the data in the original space. Then the original space coordinates or basis vectors are given here. And now we are going to split on the original space using the max cut splitting criterion. Notice the split is always along a line or a hyperspace that is orthogonal to one of the basis vectors. So let's say we get this split and we get a partition. And now that we got this partition, now that we got this partition, we split in each one, but in each one the feature space is exactly the same. So say it could be a split like that. But now let's do the same example for the pre-PCA. The pre-PCA means that in the original, in the root node, we generate the PCA, and let's say the PCA gives us these base vectors. So now when we get the split with the max cut, we get something like that, which is orthogonal to one of them. And then we split with respect to that, and we get these are the same coordinates. So we repeat this again. So this is what we could do at depth 1 of the decision tree. Now, with the local node PCA means at each node of the decision tree, we are generating again the PCA. So here at the root node, we get this PCA, we get, say, this split, and now we split it into two, and for each one of these, we generate a PCA. So these two are going to have different space representation. And now we do the splits, and the splits, these two are not necessarily parallel to each other. In the third one, to illustrate the third one, here we take the PCA of the means. Because there are two classes here, or binary classes, we are going to get two means. The not in class of A is the mean of everything else, which in this case is class B. So this is the mean of the observations or objects in class not in class B, and this is not in class A. So we just get two vectors, and for these two vectors we find the PCA. We proceed with getting the split for this space. And now, once we split it, we compute for each one the not in class means. So we have two vectors here and two different vectors in this node. And now again, we calculate the PCA for each one of these, and we get that, and then we get what looks like different splits. So altogether, we are going to look at 8 algorithmic combinations. So we have, for the split criterion, we are going to compare the Gini Impurity criterion with the max CART. And in terms of the feature space representation, we are going to use these 4 types: the original, pre-PCA, local PCA, and local means PCA. And each combination is an algorithm in blue that we are going to try. So we are going to try 8 algorithms here and illustrate for you the same example. But just before we go to the example, I want to comment on the complexity of the split. So with the original, the Gini takes dn log n, where d is the dimension or the number of features for each observation, n is the number of objects or observations. And so it takes dn log n, but also max CART takes dn log n. So the complexity is the same. The pre-PCA, the PCA is done once at the root node, and it's again the same complexity. The local PCA, before we do the split in each node, we need to do the PCA first, which is n squared times p. P in our case will be equal to d. P is the number of vectors, or principal component that we will choose, but in our experiments we used always p equal to d, to the original dimension. And it's the same for max CART. It dominates everything else, the PCA, and as it will turn out, this takes the most amount of running time. And the local means PCA, because there are only there are only k classes and k vectors, it takes d squared times k, but in the complexity analysis everywhere here we assume that the number of classes is constant or of 1, so it's these are the complexities. So these are the same for both Gini and max CART. There is no difference here. So here is the illustration of the different 8 algorithms. So row 1, the top row, are all the Gini algorithms, and row 2 are all the max CART. The first column is the original features, the second column is the pre-PCA, the third column is the node feature PCA, and the last column is the node means PCA. So let's see how it progresses at each one of these. So this is the first CART at depth 1 in each one of these, and this is the second CART at each one of these. So for each one, for each part of the partition, we are going to split it further. So we get partition to 4 set, then we do the depth 3, then depth 4, and finally this is what it looks like when it is complete to full depth. So as you see on the left here, these are horizontal and vertical because they have to be parallel to the original feature space. Here they are all the same direction, which is parallel to the directions of the the principal components, the one set of principal components, but here at each node we get different principal components, and here also we get different principal components, but these are of different things. These are of the means, whereas these ones are of the entire set of observation that falls in that node. I'll switch now to John. John, please take over, and he will show you the details of the comparative study.
John, perhaps you have to unmute, or?
Yes, I probably do have to unmute. Sorry for that.
No worries.
So, as I said to myself and my cat, it appears, the comparative study that we ended up doing a comparative study to see how these different algorithms would perform. To do this, we analyzed over 20,000 synthetic data sets, both binary and a multi-class, specifically 10-class data sets, ranging in size from 100,000 100 to 400,000. And then in addition, we ran these algorithms on real-world data sets. The implementation of these algorithms, we wanted to make it as fair as possible to make time-based comparisons. So all of the algorithms were implemented in the Python programming language, and all of the algorithms were kept as identical as possible, except for the split and feature subroutines, which by the nature of the difference of the algorithms had to be different, but those we tried to keep as close as possible using the same types of NumPy vectorization tricks and the like. So to move on to the results of this experiment, we first look at the synthetic binary case. What we have here presented is the accuracy, and so on our y-axis we have the size of the training data. So this is going to range in, at the very bottom, 100 all the way up to the top at 100,000. It's a logarithmic scale on the number of training observations in the data set, and then all of these were tested their accuracy on another 100,000. The advantages of the synthetic data set is we can generate an arbitrary amount of points to get a good understanding of how well they would perform on out-of-sample data. And then our x-axis is going to be the dimension of the data or the number of features, and then that's going to go on a linear scale. And so what we can see from this is, in this case, the darker the color, the more accurate they are. So the Gini node features PCA, the Gini node means PCA, and the max cut node means PCA demonstrate much darker colors than we're getting out of any of the other algorithms, including the baseline CART. We were then able to generate statistical significance on whether or not these outperform. And what we see is when we look at the statistical significance of it, we see Gini node features, these darker colors are going to be where it's with statistically significant. We can say it's the best performing algorithm. And so the ones then we note of interest are exactly what we noticed from the other graph. The Gini node features PCA, the max cut node means PCA, and the Gini node means PCA. And so to better analyze this, we're going to take a closer look at the Gini node features PCA versus the max cut node means PCA. This further analysis is indifferent really to the max cut versus the Gini node. And so we're going to look at the difference between the feature representations. And what we can then, I highlighted the wrong one, but what we see here is that the difference between, what we present here is the difference between the max cut node means PCA versus the Gini node features PCA accuracy with 95% confidence interval. And what we see is there's a specific pattern, and we notice this pattern that occurs throughout, is that as the dimensions of the data set go up, or the number of features increase, then the node means feature representation consistently moves towards outperforming, and much more significantly outperforming than it was ever outperformed by the node features representation. We then also look now towards how long these actually take, so the running times. And what you can note here is that the node means feature representation does produce significant speed up compared to the baseline implementation over here. So these are all relative to the baseline Gini features implementation. And it's also important to note here that where the node features was outperforming was in this top area over here, which is exactly the same area that's now taking significantly longer computationally. But the node means implementations don't suffer from this significantly longer computational time for the higher number of data observations. We then move to trying to analyze how susceptible these algorithms are to noise, since that's one of the things that can happen. And so to do this, we look at both informative features and uninformative features. Those that we call informative are going to be the features that contain information relevant for classification, and the uninformative ones are the ones that do not contain information relevant for classification, i.e. they are noise. This is one of those advantages of using synthetic data sets, is that we can directly control which ones are informative and which ones are uninformative. So the results of this analysis show that the node features, the node means, the node are still going to be outperforming, again, darker better in this case, compared to the baseline implementation. And for these specific ones, we use the training test size of 10,000. So we see that the algorithm does appear to be robust to the addition of some noise features in it. We then move now on to the generalization of this to multi-classification. And what we see here is that the scale is again going to be size of training data and dimension of data on X. One thing to note here is that it's not a perfect logarithmic scale. We go from 100,000, 10,000, 100,000, and then 200,000, 300,000. Increasing that logarithm much further was computationally infeasible. So we continue it with 200,000 and 300,000. And what we see here is we get that same pattern with the Gini node features PCA, the Gini node means PCA, and the max cut node means PCA outperforming what we have on the other algorithms, including, again, the baseline CART implementation. And the statistical significance on this one shows that with statistical significance, the max cut node means PCA is going to be dominating basically all the other algorithms in this multi-class classification in the higher regimes, and it's undecidable in most other cases. So we then wanted to make the same comparison just between the Gini node features PCA and the max cut node means PCA we did in the binary case. And so that's what we present here. And again, as I mentioned before, we do see this pattern reappearing throughout. And this is another case of it, whereas the dimension of the data increases, the use of the node means feature representation appears to have more and more significant benefits. This is then the other. Now we want to turn to the difference between the splitting criterions of either the Gini node or the max cut, to try to understand on that front. And so what we have presented here is a histogram of the max cut node means PCA accuracy, but this is across all of the data sets in the 10 class that we studied, and then we normalize them with respect to the accuracy of the Gini node means PCA. So anything above 1 means that the max cut outperformed the max cut outperformed, and anything below 1 means the Gini node outperformed. And you'll see here in this gray line, marked 1, that we see that the max cut tends to outperform the Gini representation. We then now continue to look at this CPU time, as we did in the binary case, and we see that once again the max cut, the node means representation, produces significant computational advantages over what we have from the baseline CART implementation. And then as to the robustness to noise, the way to read this one again is going to be on the y-axis, we have the number of the uninformative features, and then on the x-axis, we have the number of informative features. So what we see here is that, again, as the number of informative features or the true dimension of the data increases, the node means PCA is going to continue to dominate more and more significantly. But the other interesting thing to note of here is that as the uninformative features are increasing, we also see that in this case, the node features doesn't survive as robustly, but the node means implementations do survive robustly to the addition of these uninformative features, most likely due to the normalizing, the effect of taking the averages. So then after analyzing those on our synthetic data sets, we look at how these will perform in real-world data sets. To this end, we present 3 of the real-world data sets that we analyzed, specifically MNIST, CFAIR 10, and CFAIR 100. These are all fairly high-dimensional problems, image classification specifically, with classes ranging from 10 to 100, and objects about 60,000 or 70,000, and high amounts of features. So the MNIST data set, what we see from this is that the accuracy that we get from the baseline CART implementation is 86.9%, and then we baseline all of these with that being R1, and then everything is going to be relative to how long it took for the CART implementation to run. And in this case, we see that the max cut node means BCA is going to be the most accurate at 92.4 for a single tree, and then the time it took was 9.3% of the time the Gini features. So we see the significant computational advantages that we saw in the synthetic analysis, as well as the increased accuracy. This continues to CFAIR 10, where the baseline implementation got 26.2% of the classification correct, where max cut node means PCA, our algorithm produced 34.9% accuracy, and also again has a significant computational advantage, taking only 7.5% of the time that the CART implementation did. And then lastly, for CFAIR 100, the accuracy for the CART implementation was 8.3%, which is then compared to our implementation at 12.4%. So that's, again, we have a significant accuracy increase in this case. And then also, as we've seen throughout, the amount of computational time drastically decreased, taking only 6.1% of the computational time. So we want to now see how in the previous analysis, we were using very similar implementations to try to make time-based comparisons as clean as possible. But now we move towards analyzing what this would mean in actual implementations. And so to that end, we implemented max cut tree, which is a package using Python. We then compared the CPU time required to train a decision tree using this max cut tree package compared to the commercial quality scikit-learn implementation, which is one of the standard implementations used in Python. And so what we get from this is that on the MNIST dataset, our algorithm takes 2.91 seconds compared to the scikit-learn, which takes 9.39 seconds, contributing to a 3.2 times speed up. For CFAIR 10, we had 20.65 seconds compared to 2 minutes and 6 seconds, accounting for a 6.1 factor increase. And then CFAIR 100, we have 57 seconds to 6 minutes and 33 seconds, accounting for a 6.8 factor increase. So we see significant computational advantages against even commercial grade software. But we move now on to more recent analysis, which is on the random forest, since decision trees are useful in of themselves for classification, but a more powerful classifier that's commonly used is the random forest, which is an ensemble method that is created by training multiple decision trees. Each of these trees is trained on their own random subset of K features and a bootstrapping of the training examples. So we do experiments to see how random forest classification algorithms work with the max cut tree as the underlying tree versus how they work with the scikit-learn variant. So that's just your traditional CART variant. And then throughout these experiments, we report the accuracy as a function of the hyperparameter k. And then k is going to be the number of features randomly selected for each tree to train on. So this is going to be something that is selected by the data science practitioner that is based off of the data set, and it's a hyperparameter that can be tuned. So in the case of the synthetic binary data, we present the results for, if you remember back to those boxes at the very end, we report the result for the top right-hand corner. So this is going to be a 50-dimensional data set with, in this case, 100,000 training size. And then we also tested it on 100,000 test observations. And then all of these use 100 trees. And what we see here is that the green, or the top line, is going to be the max cut forest, which is going to dominate performance-wise past the about 8 number of sampled features. But again, that's a hyperparameter that can be tuned and chosen, so you're able to always operate in this regime over here. And it outperforms the baseline implementation of a random forest. And then for reference, we have the single max cut tree and the single CART tree. Now, so we see that the performance benefits do extend in this case to random forest. And we also now look at the CPU time. In this case, the CPU time becomes a little more interesting based on the fact that the max cut forest actually decreases in computational time required as the number of sampled features increases. This is contrary to what we would intuitively think, since each of these splits is now over a larger dimensions, and it should be increasing. But what we find is that the size of the tree and the number of splits that have to be made drastically decreases as the number of the sampled features is increasing, attributing to the decrease in the running time, where the traditional baseline CART implementation does what we expect, with its computational time increasing as it goes. But what is important to note is, again, that was a hyperparameter we could choose. So when we choose the best hyperparameter for both of these, which are marked here now with an X, what we see is in that case, we do have a computational advantage to using the max cut forestry, as well as the accuracy benefits that we saw over there. So we then continue this analysis to the case of the 10 classes, the generalization to multi-class. And again, we see that the max cut forest does still provide the highest performance benefits compared to the CART baseline implementation and then the single tree implementations. And in this case, we then will also see the exact same pattern for the CPU time, except in this case, we still see the decreasing CPU time for the max cut forest and the increasing for the CART. In this case, the comparison becomes less clearly in max cuts forest on a CPU basis. But what we can then see is when we look at the maximum achieved accuracy for the hyperparameters, it is fairly close with CART forest benefiting. But if we take a quick peek all the way back at here, even at the very lowest level of the highest number of sampled features for the max cut forest, we are outperforming even at the best for the CART forest. And so at that point, you can see that that is going to be this marker over here at the very end. So if accuracy wasn't the utmost importance, you can still beat the CART forest with comparable running time. So in conclusion, what we see is that the max cut decision tree uses two modifications to CART methodology for constructing classification decision trees. First off, uses the local mean PCA's representation for the features space, and then the max cut criterion for determining optimal splits. Together, we see these modifications result in significant improvements, both in accuracy and a significant decrease in computational time. And then initial experimentation that we have done demonstrates that extending the max cut tree to random forests are likely to result in similar improvements. Thank you very much.
Thank you very much, both of you. It has been a pleasure to see your presentation. I believe that we already have questions. Is that the case, Itamar? I see a hand raised, Itamar.
You hear me now?
Yes, we can hear you. So
Okay.
if you pose your question.
No, I can say it in simple words. Very naively, a pre-processing with SVM, pre-calculations, may ease and make more efficient the whole thing, no? Support vector machines, classification, clustering, before the classification.
Thank you for your question.
Yes, I'm not sure what you are suggesting. We are looking here at decision trees. No, there is no comparison in this study made with the vector machine. I'm not sure what you're suggesting.
Yeah, I could be wrong. That's why I say very naively. But even a tree, decision tree, can be classified for different branches' importance or relevance.
That sounds like a good idea, but at this study, we don't know how something like that would have performed. This is something that might be worthwhile studying.
Yeah, you're focused, I understand.
Yeah, we are focused here only on decision tree because in general, random forest, that's a very kind of loose statement. But in general, random forest as a machine learning technique is a very effective machine learning technique that is hard to beat. And even compared to neural networks that require a lot of training. So the purpose here was only to focus on decision trees and random forest technique.
Okay.
Thank you, Itama. Thank you very much. We have another question. Jorge, would you like to state the question? Otherwise, I can read it from the chat. Okay. Okay, so I will read it. So thanks for your talk. This is Jorge Martin from UNED University. How does the MaxCAD handle categorical or discrete predictors, like, for example, zip codes? Thank you, Jorge.
I can answer to that. I can answer to that one. The way we did it in some of the analysis that we looked at was we used one hot encoding to embed it using 0 1s, and then just treated those as continuous values, and we still had performance benefits.
Thank you very much. Is there any other question from the audience? So I had a question. So you also handle random forest implementation with your methodology, and because your methodology is already quite strong for a single tree, have you observed that actually you can build a random forest with fewer trees?
John, maybe you want to comment on that?
I can comment on that. What we do see is it does, again, pick up fairly rapidly, as you mentioned, based off of the benefits. I didn't do too much analysis, so I can't too heavily concretely comment on it. But from what I do remember of just looking through the data, it does pick up steam faster. but then it still takes a while to actually converge to not getting any benefit from adding more trees to it.
Thank you. Is there any other question from the audience? I have another question. So because you have this distance between features, could it help to define a kind of a similarity, say between between these features that you are handling, so that you can reduce the complexity of your tree?
I'm not sure what will reduce the complexity, but because one idea that is central is the use of PCA, we are not using PCA to reduce the dimension, but we can, for instance, just take the 4 or 5 leading principal components, and therefore we'll have to test only 5 combinations of features instead of the original could be 1 million features. So in a way, the PCA, I think, is one example of capturing what you are suggesting, the importance of the features. So here, but it's not exactly an importance, it's the importance of some linear combination of the features. Actually, a future work that we are beginning now is to use the max-cut decision tree with the variance of the feature space representation to derive feature importance, which we plan to use in other contexts. So the CART decision tree, there are several procedures to derive feature importance based on that, and we are going to see whether feature importance based on this could be useful and helpful. Also, I want to add that this idea of the means of not in class to do the PCA on this as representation of the entire class, objects of the same class, is very powerful, and we don't have theoretical justification for it, but we think that it captures the differences between each one and the complement classes in a way that others cannot, and it has the advantage of reducing the dimension in a fantastic way. I mean, we end up only for K classes, only with K means to work with them, so that it makes it very easy. So yeah, at this point, running time is not an issue, and there are trade-offs. So for instance, when we increase the number of features in the random forest, the max cut random forest works faster and gives better accuracy, and we think that this is because it tends to fathom the tree much earlier and have fewer nodes in the tree. We'll have to invest some research to figure out whether there is a theoretical result there or this is something that just happens in practice. Yeah.
Thank you so much. Thank you. Well, I think we are coming to the end of today's talk. We are again grateful that you both joined with such an interesting and these very competitive computational results. Just for the audience, I would like to say that there is one more seminar coming It will be on June 7. And after that, we are not going to stop. So we decided to have a second season, and we will start after the summer. And you can see already that we have gathered some colleagues to agree on giving a seminar. So we will start with Coralia Curtis, continue with Tias Gans, Leo Liberti, Andrea Lodi, Christine Pagel, and Thibaut Vidal. I have placed them on alphabetical order, but actually Coralia is the one that will start season 2. So I'm quite happy to see so many of you coming and so many of you listening to our videos on YouTube. And yes, thank you for your support. It's because of you that we decided to continue our second season. Thank you all, and thank you, Dorit, for coming today, and thank you for John to join today too. Bye-bye, everybody. See you on June 7th. Thank you, Dorit.
Thank you.
It was a pleasure to see you.
Likewise.
Thank you. Thank you, John. I didn't meet you before, but it was great to see you and your results.
It's a pleasure. Thank you.
Yeah,
He actually